So far, we've built the oscillator, video basics, borders, ball counters, ball motion controls, bricks, ball and play counter, and serve logic on sheet 1, paddle logic, on-screen display, scoring, and sounds on sheet 2, the start game controls, operational latch, coinage, and credits on sheet 3, and the flip screen circuit on sheet 4. Today we'll breadboard the final two circuits, the bonus logic on sheet 3, and the empty wall detector on sheet 2. We're using the RevFX schematics today because the RevF schematics in the manual don't exactly match the RevF boards. See Part 2 or the differences document in GitHub for details. In both circuits today, we replaced 9602s with 74123s, which are not pin compatible nor 100% logically equivalent. You can learn more about replacing 9000 series TTL with 7400 series in the Chip Challenges section of Part 1. We'll start with the bonus logic. We'll need new 7486s in King 7 and Love 7, a new 7420 in Jack 7, a new 7474 in King 8, and a new 74107 in King 9. We'll be using gates from chips we already installed. We'll need a few passives and a dip switch. We also need to replace that 9602 and adjust the tie. Bonus logic is simple. We check the score's 100th digit against the configuration switches, and if met, add a credit. This is checked for each player, so if both meet the criteria during a single game, 2 credits are added. Bonus configuration is set using the quad dip switch S1 as shown in the manual. For this match line to drop, all inputs must be high, so each exclusive OR gate must be on, which means that each input pair must be different. You can see that the switches are set to on, off, off, off to give a bonus at 100 points. This seems a bit strange because this matches a score of 100. We need to think of these configuration switches backwards, in that in the on position the switch is grounded, and when off the input is pulled high. So on becomes 0 and off is a 1. If I convert these to the proper weighted value, the bits are exactly the opposite of a score's 100th digit of 1. In this configuration, when we reach 100, all exclusive OR outputs rise and the match line drops. That was pretty straightforward, but the next part is once again a bit wacky. I'll hide some of the match logic and the second instance to give us more room, and let's ignore this flip latch for now. The SR latch is set on game start, so its pre-match output will be high. The JK flip-flop is reset at the end of every scan line, so its output is normally off, and the inverted output is on, keeping the bonus coin signal off. When a match is made, the SR latch is reset, which drops its output. This JK flip-flop has a negative edge trigger clock, and with the J input pulled up and the K input pulled down, when clocked, the output will rise and the inverted output will drop. This will raise the bonus coin signal, which triggers the annoying bonus sound one-shot and bumps the credit counter. The JK flip-flop is then reset by the fall of the next H-sync. Afterwards, we're still in the 100s for a while, so the match line will stay low, the SR latch will remain off, and the JK clock will remain low. When we move into the 200s, the match output rises, but the SR latch remains off. Since there are no further matches during a game, the SR latch and JK clock remains low, and no additional credits are given. There are 2 additional safety measures in this circuit. At the end of a game, the EGL line rises, clocking in whatever the state of the SR latch is. If a bonus was given, the line will be off, and this will flow back and set the SR latch. If no bonus was given, the SR latch output will be on, and that will flow back to the SR latch and do nothing. We also have Q feeding the set line. When Q is low, we know the operation latch is off and the system is halted. The low Q here force sets the flip latch, which does nothing to the SR latch. I would have thought you would want these on the reset side to force a low and set the SR latch, but whatever. When the operation latch is on and the system is running, the high Q allows EGL to clock in the SR latch state at the end of a game. So we do have all of these settings we can use, and they basically stop at 800 because the most points you can get with 2 balls is 896. You could actually set the switches above 800 to disable the circuit because they will never match, but they say to set them all off to disable it. The game starts out at 0, so how does that not immediately generate a bonus? Since there is a match, the SR reset line is low, but the low level on the set takes precedence, so during start game the latch remains on. As soon as start game rises, the SR latch output turns off, dropping the JK clock. This should trigger the JK, but this all happens while H-Sync is low, holding the JK in reset. Since no other high to low transition of the SR output would take place during a game with all switches off, bonuses are basically disabled, just like my career. Well, that was a lot of talk and no action. I configured the switches for a bonus level of 100 and also temporarily tied this points per brick input to give every hit an extra 8 points to save time. Start a game. And we get that beautiful sound when we cross 100 points. Not going to test any other level, but I will turn that off so I don't scare the crap out of myself. Part of what I just showed you is a lie. We were working with the RevF schematic, which shows that this bonus coin signal joins the regular coin signal in this NOR gate to bump the credit counter. On the actual RevF boards, the coin feed is hooked to the one-shot's output. Another way we can see this is that the coin counter does not increment until after the bonus tone completes, when the one-shot output finally rises. You wouldn't notice this delay on an arcade cabinet since there is no credit counter display. I think it was supposed to be wired per the schematic because the bonus coin is a nice short pulse, just like regular coin drops. I don't think they purposefully moved it to get extra protection from the attract line suppression without updating the schematic. We'll just leave it as wired per the boards since we consider the actual RevF boards to be gospel because they work. Last minor note, this pin on the RevF schematic was mislabeled and should be a 10. Let's throw this section into our retro schematic. Add parts. Add labels. Rename everything. And wire it up. We can't get to any bonus levels above 400 without a second wall of bricks, so let's wire up the final breadboard circuit. We'll need a new 7474 in Fox 4 and a new 74123 in Fox 3. We're using gates from chips we already installed, and we'll need a few passives. We also need to replace those 9602s and retie the triggers. In the manual they call this circuit the empty wall detect, but it's really just using the cheapest possible way to detect when the score hits a certain value, then put up a second wall. You can see here that when we extinguish the last brick of the first wall, the score advances to 448. This is the first time these 3 score bits are on, giving us an indication that we've extinguished all bricks from the first wall. And you can add up those brick points yourself to check. These bits are tested every time we hit the paddle, and if met, raises the flip latch clock for the associated player, which in turn triggers their one-shot. If you remember from the bricks video, asserting the FPD signals sets the player up's brick ram bits to 1. We can finally remove the last of our tie-off jumpers and wire these signals up. We have to hold those FPD lines while we cycle through all of that player's bricks at least once, which takes 1 frame or about 15.7 milliseconds. The RC timing was therefore set to 16 milliseconds for the 9602s and comes out to a little over 17 milliseconds for LS123s. These latches are reset when you start a game, and one-shot triggering can only happen once per game, even though these bits are on many times after the initial 448. Note that they could have used a single 9602 here because those FPD lines themselves don't carry any player-up information, but we'll leave those alone. Let's try that out. I'll be back. Last brick. And a new wall appears when we hit the paddle. For fun, let's temporarily drop that cap to a .47 mic, which should half the one-shot duration, and see if we only get a partial fill. Last brick. Paddle hit. Partial fill. Pretty cool. If we make the duration longer, we're fine as long as we stop the fill cycle before the ball hits another brick. No need to try that. Let's throw this last section into our retro schematic. Add parts. Rename everything. Add labels. And wire it up. Wow, I can't believe we breadboarded the entire Breakout Arcade game. Stupid? Probably. Cool? Definitely. We didn't have too many challenges. We only had to make one logical change, adding a single piece of wire to suppress spurious retriggering of the points per brick counter when the machine came out of attract mode. This is a huge thing, and I worried about power distribution, signal integrity, etc. Originally, we had power distribution down the middle, but it clogged up wiring, so we moved it to the top. It would have been better also to put power on the bottom, but by the time I wanted to do that, the wiring was too clogged up. I could change it, but we're done. I also had bricks disappearing intermittently. If you remember from the first breadboard video, when we wired up the oscillator, clock divider, and video counters, I put decoupling caps directly across the power pins, and then throughout the project I put decoupling caps across the power rails where convenient. A much better option would have been just to put decoupling caps directly across the faces of the chips right after we put them in. Not too pretty, but very effective. She also became way more three-dimensional than I would have liked. I started out using a ubiquitous 22 gauge solid, and when I needed more colors, I found some decent consolidated brand wire over at Jameco. This has a thinner PVC jacket and would have been better overall for the whole project. We could have also wire wrapped this. It would have been much better for power and signal integrity, but I think doing the breadboard gave us a lot more leeway to play around. They say if you want to really learn something, you need to try and explain it to someone else. My presuppositions about how many of these circuits worked were just plain old wrong, and I got smacked upside the head with that pesky reality thing. Next up on the project plan is to start designing that circuit board. But we will have one more short waylay before we get started. Thanks for watching.